Pluto is also incredibly far from the Sun, averaging around 39 times Earth's distance from it. So how could liquid water survive there? The answer may be hidden deep beneath the surface. Evidence collected by NASA's New Horizons spacecraft suggests that Pluto could contain a global subsurface ocean that has remained liquid for billions of years. New Horizons reached Pluto on July 14, 2015. Until that moment, Pluto was little more than a distant point of light. The spacecraft changed that completely. Instead of discovering a frozen, inactive world, New Horizons revealed mountains, glaciers, enormous plains, deep valleys, strange surface patterns, and evidence of geological activity. One of its most famous discoveries was Pluto's enormous heart-shaped region. This feature, known as Tombaugh Regio, became the symbol of the mission. Inside it lies Sputnik Planitia, a huge basin roughly 8,000 kilometers across. The basin is filled with nitrogen ice and contains enormous patterns created by the slow movement of frozen material across the surface. But Sputnik Planitia may also provide one of the strongest clues that something liquid exists underneath Pluto. To understand why, scientists had to look at Pluto's relationship with its largest moon, Charon. Pluto and Charon are tidally locked, meaning the same side of each world generally faces the other. Sputnik Planitia is positioned almost directly along the line connecting Pluto with Charon. That alignment suggests the region may have an unusual distribution of mass beneath the surface. The problem is that Sputnik Planitia itself contains relatively light nitrogen ice. So why would such a large basin behave as though it contains extra mass? One possible answer is hidden underneath it. When the enormous impact that created the basin occurred, material from Pluto's interior may have moved upward. If liquid water existed beneath the ice shelf, that water could have risen toward the newly created basin. Because liquid water is denser than surface ice, it could create the additional mass needed to explain the basin's unusual position. Computer simulations have shown that an underground ocean can reproduce several of the characteristics observed around Sputnik Planitia. But that is only one piece of evidence. Another clue comes from Pluto's surface. A frozen ocean behaves differently from a liquid one. If a subsurface ocean freezes, the water changes volume and the entire interior can contract. That contraction should leave signs on the surface. Scientists would expect to see large compressional features, including ridges and structures produced as the crust is squeezed. But New Horizons found something different. Across Pluto, researchers identified numerous features suggesting that the crust has stretched rather than globally contracted. Long fractures, cracks, and other extensional structures indicate that Pluto's interior may have expanded over time. That is exactly the kind of evidence scientists would expect if a subsurface ocean remained liquid or changed internally without completely freezing. Thermal models provide another important clue. Pluto formed roughly 4.5 billion years ago. At first, it would have contained heat left over from its formation. Its rocky interior also contains radioactive elements that slowly release energy as they decay. The amount of heat produced is not enormous, but over billions of years it can make a difference. Above the ocean, Pluto has a thick layer of ice. That ice acts like insulation. Instead of allowing all of the internal heat to escape immediately into space, the thick crust can trap some of it below the surface. This creates the possibility of a warm interior beneath an unbelievably cold surface. Scientists have also explored another possible insulating mechanism. Deep beneath the ice, there could be layers of gas hydrates. These are unusual crystalline structures in which gas molecules become trapped inside cages formed by water molecules. Such materials can be highly effective at slowing the transfer of heat. If a layer of gas hydrates exists inside Pluto, it could help preserve internal heat and make a long-lived ocean more plausible. The idea is important because Pluto does not have the same kind of heating mechanism found on some of the famous ocean moons around Jupiter and Saturn. Europa and Enceladus, for example, experience strong tidal forces caused by their interactions with their host planets and neighboring moons. Those gravitational interactions stretch and squeeze their interiors, producing heat. Pluto has no giant planet nearby doing that to it. So if Pluto really has a liquid ocean, something else must be keeping it warm. Radioactive decay and insulation may provide part of the answer. But there is even more evidence. Researchers have studied the fractures across Pluto's icy crust and used them to estimate the properties of the material underneath. The patterns of those cracks depend partly on the density and thickness of the layers below them. By comparing different Pluto's possible ocean could provide some of these ingredients. The water would be protected beneath a huge layer of ice. That ice could shield the ocean from radiation and the harsh environment of space. The rocky material beneath the ocean could potentially interact with the water. And if chemical reactions occur between rock and water, they could produce energy that might be useful for biological processes. This does not prove that Pluto has life. It is extremely important to make that distinction. Scientists have not detected organisms, biological molecules, or any direct sign of life on Pluto. At the moment, the ocean itself is still inferred from indirect evidence. But the fact that an ocean may exist at all makes Pluto a much more interesting target for future exploration. There is another reason scientists are excited. The ocean may not be completely isolated from the surface. Evidence for cryovolcanic activity suggests that material from the interior could have moved upward through the crust. On Earth, volcanic activity provides a connection between the deep interior and the surface. On icy worlds, cryovolcanism can play a similar role, except the material may include water, ice, ammonia, and other volatile substances rather than molten rock. If Pluto's interior has been moving material toward the surface, future spacecraft might be able to study those deposits. That could provide an indirect sample of material from beneath the ice without having to drill through dozens of kilometers of frozen crust. It would be an extraordinary scientific opportunity. Imagine finding a fresh deposit on Pluto that originated from deep inside the dwarf planet. Scientists could analyze its chemical composition and determine what substances exist in the hidden interior. That could tell us much more about the ocean itself. But reaching Pluto again will not be easy. New Horizons took almost a decade to reach the dwarf planet. The spacecraft traveled at extraordinary speed, using a gravity assist from Jupiter to increase its velocity. It then raced through the Pluto system during a brief encounter. There was no opportunity to slow down and enter orbit. Every instrument had to collect as much information as possible while the spacecraft flew past. The data was then transmitted back to Earth over many months. Even after the encounter was finished, scientists continued studying the information. New Horizons did not simply provide a few photographs. It collected measurements of Pluto's surface, atmosphere, composition, temperature, particles, and environment. Those observations continue to generate new scientific studies years after the flyby. That is why Pluto's story is still developing. A discovery made during the original mission can lead to a completely different interpretation years later when scientists combine it with new models and additional observations. And there is another important factor. Technology has improved since New Horizons was designed. Future spacecraft could carry instruments that were not available when the mission was originally planned. Radar systems could potentially investigate the structure of Pluto's ice shell. More advanced spectrometers could study surface materials in greater detail. Sensitive instruments could search for chemical compounds that might have originated from the interior. An orbiter could also observe Pluto repeatedly instead of seeing each location only once during a flyby. That would make it possible to search for changes over time. If cryovolcanic activity is still occurring, repeated observations might reveal fresh deposits or changes on the surface. If Pluto's atmosphere changes seasonally, an orbiter could monitor those changes continuously. And if the ice shell has subtle movements caused by the ocean beneath it, long-term measurements might reveal them. A future mission could therefore transform a strong scientific hypothesis into direct evidence. But even without another spacecraft, the current evidence has already produced an important shift. Pluto is no longer simply the tiny frozen world that many people imagined. It is a dynamic planetary body with a complicated interior. Its surface contains mountains made of water ice. Its nitrogen glaciers move. Its atmosphere changes with the seasons. Its crust contains enormous fractures. And beneath that crust, there may be a liquid ocean. The discovery also changes the meaning of Pluto's famous heart. When people first saw that enormous bright shape in the New Horizons images, it immediately became one of the most recognizable features in planetary science. But the heart is more than a beautiful surface pattern. Its location, structure, and geological history may be connected to the deeper interior of Pluto. The basin within the region may have been created by an ancient impact. Material from the interior could then have responded to that impact. Over billions of years, ice, nitrogen, gravity, and internal heat continued reshaping the area. What we see today is the result of that extremely long geological process. In other words, Pluto's heart may be telling us a story about what is happening kilometers beneath the surface. And that is one of the most remarkable aspects of planetary exploration. A spacecraft can photograph a surface feature millions or billions of kilometers away,